Welcome to Mrs. Carl's Chemistry Crash Course. Today we're going to be talking about thermochemical equations. Okay, we're going to be talking about delta H today. That's the enthalpy change for a chemical reaction, also called enthalpy of reaction or heat of reaction. You'll see it abbreviated like that. It's an extensive property, which hopefully remember, it's a property that depends on the amount of material we have. So the amount of heat that a reaction produces or amount of heat a reaction absorbs depends on the amount of reactants. So you're going to be looking at grams to moles, moles to grams, and remembering all of that stoichiometry is going to be important when we're talking about heat of reaction. This also means you're going to need a balanced chemical equation for every reaction we do. So let's take a look at a reaction. Okay, here's our reaction that we're going to practice with. I'll give you a moment to balance it, so I recommend pausing the video and then coming back and checking your answer. Welcome back. Hopefully that's the balanced equation you got. So what does this mean? This tells us a lot of information right here. It tells us that when 1 mole of propane reacts with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water, that 2,044 kilojoules of heat is released. So an exothermic reaction. So for those stoichiometric ratios, 2,044 kilojoules of heat is released. So let's go through and write down all of the relationships that exist. Maybe not all of them, but a few of them. So if we were to look at just the reactants, if we had 1 mole of propane, we release 2,044 kilojoules. If we had 5 moles of oxygen, we're releasing 2,044 kilojoules. So 2,044 kilojoules of heat is released when 1 mole of propane and 5 moles of oxygen completely react. So these ratios will turn into your favorite things in the world. I know they are. Conversion factors. Told you multiple times way back in first year chemistry that these are important. So these are really important. They will save you now. Also remember, these are in moles. In the lab, we don't weigh in moles, we weigh in grams. So we're going to be using molar mass to convert between grams and moles. Let's try a problem and see how well you do. The problem is going to be based on propane, so make sure you have that equation handy. Okay, here's our problem. Propane gas tank on a home barbecue contains 10 kilograms of propane. Calculate the heat associated with the complete combustion of all the propane in the tank. So what are we given? We're given the mass. So we have 10.0 kilograms. We know it's propane. You already wrote the balanced equation. So that would be your first step. So we have the balanced chemical equation. We know the heat released from it, 2,044 kilojoules, and we have a mass of 10 kilograms of propane. So what's our plan to get to the heat associated? Because that's what we're looking for. We're looking for the heat. So first thing, you're going to have to convert those kilograms to grams. And because our enthalpy is kilojoules per mole, we're going to have to go from grams to moles, so that's our molar mass of propane. And then from there, we can find our kilojoules from the 10 kilograms. So take a moment, find the molar mass of propane. Welcome back. Let's set this up as a nice long conversion problem to be solved. So we're going to take our 10 kilograms, convert that to grams. We know there are 1,000 grams in 1 kilogram. At this point, our kilograms cancel out. Next step, we're going to go grams to moles. Hopefully you found your molar mass to be somewhere in the vicinity of 44.09 grams in 1 mole. Grams cancel out, so we're good to go so far. And now our kilojoules per mole, negative, because it's released. Kilojoules, and that was for 1 mole of propane. And when you get your answer, it's a pretty big answer. So negative 4.64 times 10 to the 5th power, and our units are just kilojoules. So that's the heat associated with completely combusting the whole propane tank. Okay, here's your problem to try. As usual, it's infinitely harder than the example that I did, but use the information from the last example and all of your knowledge of chemistry up to this point. Figure this out. Here are a couple hints. 1, when you write the balanced equation, you're going to use halves in front of oxygen. So you want to make sure that your coefficient in front of butane is 1. So you're going to use something half oxygen. Okay, that's okay. Just make sure your coefficient in front of butane is 1. That'll help you out. The other thing, you're just going to work it backwards. You're going to look for the molar mass of butane, the molar mass of carbon dioxide. Okay, at this point, pause the video, try to work this out on your own, and then I'll give you some answers. Okay, you should end up with 33 grams of butane and 99 grams of carbon dioxide. Hopefully things went well for you. Do a few more practice problems out of your book, and we'll talk to you later.